Ready? Good afternoon. I know that probably you are all Italian, but as you know, we have to speak in English. And I must say that I would have some problems in lecturing these topics in Italian because I'm not sure the terminology, I studied directly in English. So, okay, so let's. Okay, so this is our web page, which you know. And so we now are moving forward to the next lecture, which is dedicated to forcing estimation for Harbour design. The lecture is here, and there is a PowerPoint in the bottom, which I already downloaded. As usual, I will use the PowerPoint for my lecturing, and I will once in a while jump over the web page to make sure that I don't forget anything, because as I told you, the PowerPoint is very condensed. It's just a synthesis. So the PowerPoint is here. And so what is this topic about? It's forcing estimation is a central step in any engineering project, in any design project, which of course any project needs to be based on an estimation of the forcing, of the loads, of what we may call, with a terminology that is not very well consolidated in English, design variable. It is very consolidated in Italian, variabile di progetto. Design variable in English is not really a good terminology. Usually they are called loads or forcings. And when we talk about harbors, and when we talk about all the structures that we need to design, we need to size in an harbor, of course, there are several forcings that need to be estimated, because we may talk of sizing, for instance, the size, the dimensions of the harbor in a way that allows the ships to maneuver quickly and also to maneuver when there are unfavorable conditions, like very strong waves. We may have to design the berths, and we may have to design the mooring points of the berths, and the berths may be subjected to many loads from the sea, from the land side, from the moored ships, because also when the ships are moored, to moor a ship means that the ship is fixed to the berths through some points where we put a rope connecting called mooring lines, and we put a rope, a mooring line around these points where we want to fix the ship. And therefore, once the ship is moored, of course, the ship delivers a forcing alone over the mooring point, which is transmitted from the mooring point to the berth. And then we may have to design and to size the structures over the berth. If we have buildings for the port authority, for any kind for stocking goods, these buildings need to be designed, and of course, we may need to estimate loads that are coming from the sea. And if we have to put there cranes in order to load and upload the goods, of course, you have all an entire set of tools, of accessory tools that you need to also design, based on the estimated loads and estimated forces. So the problem is really, very, very diverse, involves a diversity of sub-problems. We will not focus on everything we need to estimate design variables for an entire port design. In particular, we will focus on the loads from the sea, and we will discard the loads from the land. We will not consider these loads because usually they are estimated in geotechnical engineering. geotechnical engineering. And these loads are, for instance, the pressure by the soil, the filling material that we use to fill up a berth. And if it is a closed berth, for instance. And another load that comes from the land is due to the traffic. And there is a shear stress given by the traffic. And there is also a vertical load given by the traffic, because, of course, trucks are very heavy. And we will not consider these loads, which are usually dealt with in geotechnical engineering. We will consider the loads from the sea, as I said, and we will not focus on the sizing of gravity walls. We will not focus on the sizing of cutoff and sheet piles. Let me just show you what is a cutoff barrier. We already mentioned it. And a cutoff barrier is an infrastructure that is used when we need to construct a continuous watertight barrier capable of accommodating some movements and deformations. I think there are some more pictures here, but you can see a cutoff, for instance, here. The brown wall is made with a cutoff. And this cutoff allows, in this case, to contain the soil that is behind the cutoff in order to resist to the pressure given by the land over this coastal area. I think this may be a railway, as I can understand from this video. And we will not focus on the design of cutoffs. We will not focus on sheet pile design. So what is a sheet pile is a foundation like this one, a foundation which can be used to sustain a berth. Again, these infrastructures are usually, structures are usually the subject of geotechnical engineering, and therefore we don't want to overlap with it, okay? Perfect, but if you are interested, maybe in getting information, there is this reference, which I already mentioned to you, the Port Designer Handbook. It deals, I forgot to update the link, and you may remember that we found it on the web by Googling. It's Port Designer Handbook. And this is freely available. If you search on Google, should be here, but there are some that are not free. Let me see if the first link is free. Anyway, this is something that is available at least in previous editions, available on the web. Let me see. This one is not for free. You see the price is quite heavy, but there are previous editions which are available. I need to remember to update the link. Anyway, in this designer's handbook, it is also treated the design of cutoff and sheet piles, if you are interested. And basically, many of them are empirical formulas that are used. And this is another reason why I don't really like, just 1 second, I'm trying to close this window and I can't get rid of this taskbar. Okay, no problem for now. This is why also I'm not, the reason why I'm not also dealing with these problems is that, you know, basically we solve the related design with empirical formulas, and therefore I prefer to concentrate on the things that are supported by a conceptual understanding of the processes. What you see here is a figure of a mooring point, and precisely this is called a mooring bollard. Before I move forward, I wanted to focus on some terminology because, of course, in order to understand each other, we need to know the terminology. I would like to give you a reference for a glossary of nautical terms, which is freely available. And let me just see here. 1 second. Can't find. Okay, here it is. The reference is the glossary of nautical terms that you find in Wikipedia. And here there is everything you need. So if you are in doubt with the meaning of some terminology, just look here. And it is very easy to search for terms. So for instance, if we want to know what is the beam, what is called the beam, we go down here, and here there is the beam. The beam is the width of a vessel at its widest point, or a point alongside the ship at the midpoint of its length. So basically, it is the width of the ship, which can be measured by taking the largest width, or the width, a point alongside the ship at the midpoint of its length. So you can go in the middle of the ship and you measure the width, or you take the maximum. And this is the beam. And most of these terms are linked to a figure. And you see here a specific Wikipedia page on the beam, and the beam is B. Okay. So, and this is called precisely the beam at waterline. So it is measured at the waterline. Keep in mind that when we refer to these terms, there is sometimes some flexibility depending on the language, depending on the country where they are mentioned. There might be some flexibility. A first example of flexibility is when I said you can measure the width by taking the maximum or referring to the midpoint. And in this case, you see that the width is measured at the waterline, and therefore they call it beam at waterline. Okay. Now let's go back to our figure here. I can take it from the PowerPoint presentations. And here there are some terms that I would like you to try to remember, because we will use them several times. So the beam is one, okay? And also the length overall of the vessel, and the length overall here is OA. It means the max length of the vessel. This is extremely important because depending on the max length of the vessel that you are expecting, you have also to size the berth, as we said, by sizing a longer berth than the max size, of course, of the vessel that you are expecting. The waterline length is what is called here WL, okay? W for waterline and L for length. And then there is what is called the length between perpendiculars, which is PP. We will not use it. And it is defined in the way you see sketched here. It is rarely used. Usually, indeed, we use the length overall and the waterline length to characterize the longitudinal dimension of the ship. Longitudinal means along the ship, and transversal direction is across the ship. Important is the draft. So this term here, I'm not really sure of the pronunciation because it depends on American English and UK English, but I am quite sure that at least in UK English it is pronounced like draft, okay? With to take it distinguished from drought, which means water scarcity, okay? And then the freeboard, which is depicted here. Where it is placed, the waterline, of course, the waterline depends on the load of the ship. When the ship is fully loaded, of course, the waterline goes up. Usually, the waterline is defined at full load. Okay. Of course, when the ship is unloaded, the water line goes down, but keep in mind that another term that we will use, when the ship is fully unloaded, usually they load ballast. What is the ballast? It's a weight that is loaded very frequently in a ballast tank by loading water. So when the ship is unloaded, what they do, they have a tank that they fill with seawater. Why? Because otherwise the ship may get unstable. Because of course, if the water line goes too low, then there is the problem that the ship may be unstable and may sink. Defining the stability of the ship was it's a classical problem in naval engineering. Just to inform you that in the Middle Age, when they started to build very huge ships, and also in ancient periods, the stability of the ship was a real problem. And usually they moved forward with trial and error. Like you try, and it happened that in Stockholm there is a ship conserved in a museum that goes back to the Middle Age. It was a ship that just after putting it into the sea, they made like 200 meters, and then the ship flipped and sank. And they took it back from the sea very recently. This just to mention that it is indeed a classical problem in naval engineering. We will not study it because we are not dealing with naval engineering. And of course, they know, based on engineering design, when it is the time to load some ballast. Okay, this is just a start. So let's start by talking about the mooring loads, which are loads that come from the sea. You may remember that we discussed last time a sketch, the loads coming from the sea, coming from the land. Mooring loads come from the sea, and they are originated by the mooring lines, which connect the ship to the mooring points. The mooring loads can be originated by wind hitting against the ship, and this is a relevant force. It's definitely the more relevant. It's even more relevant than the mooring load originated by waves. When I talk about mooring loads originated by waves, I don't mean the direct action of waves against the berth. I mean the action of waves against the ship that is transferred to the berth through the mooring lines. And then there are the currents. The currents, same thing. The currents tend to move the ship, and therefore an additional forcing is transmitted to the berth. When we want to estimate these loads, of course, we need to start from a C variable, like defining the expected wave height with a given return period. This is a problem that you need how to solve, because you, with Professor Archetti, already studied how to estimate an expected wave height, wave frequency, wave period for a given return period. So you are already familiar, correct, with the terminology return period and extreme estimation. Perfect. So we have to start from the wave behaviors, or the wind behaviors, or the current behaviors. And these behaviors are usually defined through statistics. So keep in mind that, as nasty as it can be, statistics is the basis here, the basis for our engineering, because all of these behaviors cannot be defined in deterministic terms. You have to define them statistically, either when we talk about wind, when we talk about waves, when we talk about currents. We will not consider in our discussion the berth load originated during berthing, which means during the approach phase of the ship. And these loads are originated by the fact that when the ship is approaching, is moving, and therefore, when it gets moored, there is some kinetic energy related to the movement of the ship that is transmitted as a load to the berths. And these loads can be caused by the usual conditions, because, of course, a ship is approaching with a given velocity. can be also caused by extreme events like a mistake in maneuvering or like maneuvering in very unfavorable conditions. And therefore, we will not consider these. I will make a very quick mention. Usually, they are estimated by using empirical formulas. Okay? And this is another reason why I'm not considering them. Instead, for what concerns the wind, waves, and currents loads, we will use a very similar approach for them, very similar. And it is an approach that is conceptually based, and for this reason I like it, because it allows us to benefit from our understanding of what happens when wind blows against a ship and then the ship moves, but it is moved and therefore a forcing is given to the berth. It is, they are conceptual relationship, but at the end of the story, there are some parameters, you will see, some coefficients, in order to account for uncertainty and in order to account for the fact that there is unavoidable uncertainty when you deal with a behavior like wind that is defined statistically perfect. So, first of all, let me give you some numbers, some guidelines, some rules of thumb, okay? So what kind of order of magnitude of loads are we talking about? So, of course, we have to start by defining what, the behavior of the ship that we are expecting. So, just 1 second, I want to make sure that I activated the micro. I am pretty sure that I activated it, but let me just check. Yes, it is activated, sorry for that. Okay, so let's start from the ship. So for a design ship, and we have to talk about a design ship, an expected ship, okay, up to a tonnage of 20,000 tons. Each mooring point can be designed so that it resists to the following minimum loads: horizontal pull ranging from 10 to 100 tons, depending on the ship displacement and type of load, of course, but we are talking here of an order of magnitude. You see that there is a factor of 10 between the minimum and the max of this range. And to give you an idea, if you make a simple ratio between 100 and 20,000, you get an idea of the ratio that converts the tonnage of the ship to an horizontal mooring load. The vertical load, the vertical pull, it's about 0.5, half of the horizontal pull. And we assume that they may act at the same time, of course, because when you have wind, you have also waves, and therefore the waves cause kind of up and down the ship, while the wind is an horizontal load. And therefore we cannot assume that they are not occurring at the same time. They are very likely to occur at the same time. The pull load should be considered occurring shipward at any angle with the berth in front to select the less favorable condition, because as we will see, there are mooring lines that are connected perpendicularly in a perpendicular direction to the berth line. There are mooring lines that are connected at an angle, we say, so they are not perpendicular. So if you have wind against the ship, of course, we will see that the angle of the mooring line makes a big difference in terms of the resulting forcing. So we have to consider any angle within a range. We will see what is the typical angle of the mooring lines, not really any angle starting from zero, but in a range, as we will see what is how it's defined. Okay. Okay, good. Now, for design ship of more than 20,000 tons, displacement, the The assessment of the mooring loads should be carried out by considering all possible forcing operating at the same time. What does this mean? It means that the possible forcing are the forcing given by wind, by currents, and by waves. If you have a ship with a very large tonnage, we have to assume that these loads can be concurrent, because even if they have different time scales, and the current is varying with a different time scale with respect to the wind and with respect to the waves. The time scale of the wind is in a way related to the time scale of the waves, but for the current, the time scale is different. But even if the time scale is different, very large with the ships, we assume that they may occur at the same time. And here you see a reference where I found these recommendations, these orders of magnitude. I think the orders of magnitude are extremely important. Of course, they are not very useful for the finance, but for getting an idea, they are extremely important. I insist a lot with the students on getting a clear idea of the orders of magnitude. They are also important when you dialogue with your colleagues, with the stakeholders, because you understand that if the stakeholders realize that you have no idea of the orders of magnitude, it's a problem. So to the students of water engineering, I always say, look, you have to know what is the rainfall depth occurring over Italy in 1 year, not the precise value, which is varying, by the way, from the north to the south, but in order of magnitude, you have to get it, because otherwise you cannot talk with anybody about water engineering if you don't have a rough idea of how much rainfall you may get. So to you, I say, you have to have an idea of this forcing, a preliminary idea of the order of magnitude, because if people realize that it's completely, and it is also important because in this way you can prevent what we call accidental mistakes. So if you make a clear mistake in computation, and you look at the result, if you're able to recognize, because the good thing of mistakes is that usually they don't give you an estimate that is close to the true one. Usually they give to you a completely different estimate, a completely different final result. So if you have the capacity, the capability of understanding by eyes immediately that there is something wrong, of course you will be in a safer condition. Don't worry if you don't know what is the rainfall, accumulated rainfall depth in Italy. By the way, it's 0.8 meters in a year. Okay? This is the average rainfall over Italy. And in the north, you may get up to 2 meters of rainfall. In the south, down to half a meter. This is the range. But don't worry if you don't know it. But it's important that you know the numbers of Harbour engineering, of course. So all forces. So we have to characterize wind. We have to start from wind. And how to characterize the wind? Of course, through measurements. And we will see there are precise rules, standards for measuring wind velocity. Wind velocity is not constant usually. You don't get a constant wind. You get a wind velocity that is varying. There are gusts. The gusts are the strongest episodes of wind velocity. And then you may have, even within a windstorm, you may have some seconds, even some minutes where you don't have any wind or the wind velocity is very low. As I said, we need to characterize it statistically. So we start from the data, we start from the observations that are collected by following precise rules. And first of all, how is the instrument to measure wind is the anemometer. And the anemometer, it's placed at an assigned height over the ground, which is usually the standard is 10 meters. And it should be specified. So when you collect the wind data, in the metadata, which means additional information regarding the data, you should find the height of the anemometer. Today, the good thing is that for this kind of weather variables, because wind is part of the weather, and let's say the wind at a short time scale is part of the weather, for this kind of weather variable, we have an increasing availability of observations which are open access. nowadays because several funding agencies require openness of the collected information. Just 10 years ago was not like that. If I go back only 10 years, it was very difficult to find free data. Still, I mean, some data are proprietary. We use this term. Proprietary means that they are owned by somebody or some institutions, which is, I mean, justified because taking data is expensive, and therefore the institution that put the funding in it, they need to get, in a way, reimbursed by the expense. But on the other hand, sharing the data, it's something that is extremely important. So if you look over the web for wind data set, you see the data set of the global wind atlas, very interesting. And let's see. By the way, the global wind atlas, it's also used for producing wind energy. And or I would say that this is the main, you see here, is part of the global solar atlas, energy data info. So it's not the same type of data that we need in coastal areas. Some of them can be used. And also here, there should be a map somewhere. Bathymetry. You see that there is also some data on bathymetry. Anyway, viewfinder panoramas. Okay. But this is the viewfinder panorama is a global data set of digital elevation model which describes the shape of the land. And I think it is here, global atlas of siting parameters. Anyway, just wanted you to know that there are several sites where you can find this data. And this data, or let's say, you see that there are also several videos on how to use it. And the list of open data wind turbine data set. This is in GitHub, so it's fully open. This is the new European Wind Atlas. And let's see if this is more accessible, more immediately accessible. Here there is a map, so probably there is welcome, okay, I am an educator, good. So here you see a map which is clickable, and then you can see what are the variables that are available, horizontal wind, and here you see a terminology that gives to me the opportunity to clarify to you what is the difference between climate and weather. Weather is the day-to-day or hour-to-hour data. Climate is averaged over a time window that is assumed to be at least 30 years usually. So when we say climate means wind velocity over 30 years, which is useful for designing, for instance, wind turbines. It's not very useful for designing wind forcing against ships. But when you, what I wanted to say, when you download this data, try to understand by looking at the metadata, how are the data collected. When you use data, you have to get a good knowledge of what you are dealing with. So what was the instrument, the height of the instrument, of the anemometer, what is the expected uncertainty, what is the time scale, it is measuring wind, how many times, it's hourly measurement, it's minute measurements, or it's seconds. You have really to get a good knowledge of the starting point of the data. And you have to know everything is possible with it. Okay, because of course it is conditioning the uncertainty of your final result. So once that you have the data, you have to elaborate them statistically. You have to describe the probability of getting a given, in the site of interest, a given wind velocity and a given wind direction, because it's not only possible. it is also a matter of consideration. It is also a matter of consideration the direction of the wind. Keep in mind that we try to align the berth with the dominant current direction, and if it exists, a dominant wind direction. Because of course the wind is less dangerous if it hits the ship in the longitudinal direction, because the area of the ship, the transverse area, is much lower than the longitudinal area of the ship. So if you get the wind perpendicular to the longitudinal direction of the ship, the wind hits a very large area of the ship, and therefore the pull against the berth is much larger. So the wind direction is extremely important. So what is the wind rules? Okay, let's open it. Wind rules here cannot be opened, so let me just go to my website. Here, the wind rules. First of all, there are figures here, but let's look at the wind rules. Okay. So what is a wind rose? Let's look here. A wind rose is a diagram used by meteorologists to give a synthesis, a synthetic view of how wind speed and direction are typically distributed at a particular location. Okay. Okay, good. Here there is a figure that I copied in my website. Okay, here it is. Let's get it in PowerPoint because it's the same figure. Here it is. It is a wind rules at LaGuardia Airport. Of course, the wind is also extremely important in airports for obvious reasons. What is a wind rules? It is a statistical representation in terms of probability of wind speed and wind velocity. So here you see, first of all, the circle at the center, 3.6%. It is the percentage time of calm weather, no wind. So it means that in the long period, if you get observations for a long period, you get 3.6% of these observations with zero wind. Okay, perfect. This is fine. Now, let's look at the south direction. In the south direction, you see that there is a long bar that is shifting in different colors. Starting from calm, look at the bar, at the vertical bar on the right. So calm is 3.6%. It is light blue here. It's not depicted in the vertical bar. And then you have the velocity of wind that is varying from 0 to 1.54 meters per second in light blue. Dark blue is the range between 154, 309, etc. By the way, the light blue here is not present, which means that probably the measurement has a scale that doesn't make any difference between light blue and dark blue. Because of course, if you have here a given percentage in the south direction, what is the percentage of dark blue? You see the percentages in the circles, and it's about 2%. Okay, and so if you have 2% of observations with the dark blue, for sure there are some observations also with the light blue, but they are not depicted here, probably because the precision of the instrument doesn't allow to get for low wind to the resolution that allows to make the difference. And then we have the dark green. The dark green is the range between 309 meters per second to 514 meters per second. And the dark green is extended up to 8%. And then there is the light green. And there are two tones of light green. Here it's difficult to make a difference, but you see that indeed the bar is split in the south direction in two tonalities of light green. And which means that you get with these two tonalities of light green to a percentage of about 12%. Okay. So the fact that the south bar is the longest means that the prevailing wind direction is from the south. Okay. In fact, you see here prevailing wind in this case are southerly and northwesterly, because the second bar in terms of length is in the northwest direction, where you see that there is this subdivision of velocities. Okay. And then there is the western direction and something in the northeast. Okay. Now, if you basically make the sum of the wind in a given range, sum of the wind velocity in a given range in any direction, you get the percentages that you see in the vertical bar. So calm situation is 3.6. This is easy to recognize also in the wind rows. And then if you go to the wind velocity of 309 meters per second, it's 22%. The 22% is derived by summing the dark blue over all the directions. So if you make the sum, you get, you see here how many directions we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16 directions. And the 16 directions with an average of about 1.5, you see, because it is between 2% and 1%. So 1.5, 16, 1.5 is about 23%, 24%, which is close to 22.6. So basically, this percentage that you see on the vertical bar are the sum for each wind velocity along all the directions. And if you're interested in the percentage along a given direction, you have to look at the wind rows in that direction. So is this clear? It is a statistical definition. And in the south direction, you get wind for 12% of time plus 3.6. Or so if you sum the percentages along each direction, so 12% plus 4 plus 6, 12, okay, it is a very long sum, but if you sum the percentages in each direction, you should get to 96.4% plus calm 100%. Okay, so it is just a description of how many times we find a given wind velocity in that direction. That's it. Okay. It is not immediate to read, but if you talk with a sailor, they are very good. If you show a wind rose to a sailor, they immediately understand what is the direction of wind that they are concerned about. So the wind rose is our starting point, and we get immediately a clear idea of the probability of getting a wind velocity in a given direction. Probability, because these frequencies are probabilities. Okay, now let me just make a box here. A box, I mean, let me open and close a parenthesis to clarify what is probability. We will have the opportunity to deal with to define this probability. We need to do that. But I know that probability usually is a nasty concept. Anytime that I get the surveys from the students, you know, in the survey there is a stupid question. What is the topic that you understood better? And what is the topic that you understood worse? And usually in the topic you understood better, there's a diversity of options in the students. But in the worst one, there is usually a unanimous opinion. It's probabilities. The students don't like probability. I understand that because I didn't like it, unless I realized that it's indeed very simple, despite a mathematical treatment that is very nasty, very complicated, almost impossible to be understood. Actually, it's very simple. It is crunching numbers, and we need to understand probability to start from a basic statement. Probability is frequency. That's it. Okay, so I cannot define it in this. I cannot define probability is frequency. It's a different story. It is not correct. But from the point of view of an engineer, probability is frequency. That's it. So I toss a coin, I get 50% of the time ahead, means that the probability of getting ahead is 50%. Probability is a number between 0 and 1, like frequency. And probability is frequency. That's it. So this is why I said, look, the windrows gives the probabilities. Now you may ask me, but if it is not correct to say that probability is frequency, why? The explanation is again very simple. Frequency is derived by numbers. And therefore, it depends from the sum. You make an experiment, you take think of same place, you get a wind speed data for the same place, but you have one set of data referred to the year 2024. Another set of data referred to the year 2023. Of course, if you compute the windrows, you get two different windrows. They will be very similar, but they are not the same because frequency depends on the data that you use to compute it. Probability is something that is computed by theory. Of course, you may use the data to refine your estimate, but probability is something that cannot vary depending on the year. It should be the same. So they have different names just because we want to remark that probability is a refinement of frequency, something that is more reliable. Because frequency, think of if you have an observation for 1 week, you cannot do the windrows. Therefore, you have to identify the probability with a different approach. But actually, if we want to be very simple in our conversation, probability is frequency, nothing more than that. And I mean, these frequencies here is what we need. Okay? And then why I need probability? Let me make this example here. You see that light blue is not there. So if I want to estimate the frequency of light blue, this data don't help me because light blue is not there. So I have to use another approach because my resolution in the data doesn't allow me to. And another thing, another interesting thing, here I got the frequency of the wind speed up to 15 meters per second. It's in the total frequency of the wind at the speed of 15.50 is 1.6%. You see the vertical bar in all the directions, 1.6%. So this number tells me that 1.6% of the time, I may expect a velocity up to 15.50. But if I want to estimate the wind velocity, the percentage of wind velocity up to 20 meters per second, I cannot use this graph here because I need to extrapolate from the data. And to make this extrapolation, I need to use the theory of probability. It is not easy because you understand if you have data collected for 30 years, where the max wind velocity is 15.50, it doesn't mean that you cannot get 20. It means that you may get 20, but with a lower percentage. And then I need to make an extrapolation And of course, it's the theory becomes a bit complicated, because while computing the frequency is very simple, then of course you need some complicated theory. Okay, but in any case, let's start from this wind rules, and the wind rules gives us the wind velocity. Okay, and okay, we already commented about this figure here. Now, and also about this. Okay, and okay, that's okay. This is interesting. So let's suppose that I want to concentrate on the southern direction, and then you can get these percentages. So the wind velocity of 3 meters per second, for instance, is not exceeded about 2 plus 3.6% of the time, where 3.6% refers to current condition. So I get the light blue in the south direction. You see that the bar reaches a bit beyond 2%. So it's 2% plus 3.6% is the percentage of not exceedance of wind velocity of about 3 meters per second. And then if I want to get the percentage of not exceedance of 11 meters per second, then it's about 11.8 plus 3.6% of time. So it is very easy to compute the percentages of not exceedance. And if I want, I can make a graph. You see, this is a graph made by myself by using the wind rules, where I computed the percentage of not exceedance over all the directions. Sorry, this is not correct. It's on the south direction. Sorry, and I noticed that after 3 years that I'm using this figure, I noticed only now that the caption on the vertical axis is not correct. This is in the south direction. So in the south direction, I have a percentage, a graph that you can see here that gives me the percentage of not exceedance of the wind velocity. You may remember from previous courses that this is also called the cumulative probability distribution. So the cumulative probability distribution is like the cumulative frequency distribution, because as I said, let's treat them as synonyms. And it is the cumulative probability distribution is the usual probability distribution that we use, for instance, to characterize wave height, that can be used in characterizing wind velocity. I think Professor Archetti may have told you that wind velocity is usually, wave height is usually computed, extreme wave height, with the Gambian distribution. Correct? You studied the Gambian distribution. Yeah, for wind velocity, the distribution may be different. Because, of course, different variables may need different distributions. When you compute the frequency, the procedure is the same, but the probability distribution is an analytical interpolation of the frequency, because it allows us also to make extrapolation. And therefore, the analytical representation of like this picture that you see there, this graph, may be different by a good analytical representation of extreme wave height. Okay? Even if, in most of the cases, you may apply the Gambian distribution also to describe wind velocity. Okay. So in this way, what we can get is a probability of not exceedance of a given wind velocity. Probability of not exceedance is the complement to one of the probability of exceedance. Okay. So if I get from here the indication that I have a probability of not exceedance of about 15.6% of a wind velocity of 11 in the south direction. It means that the probability of exceedance is 100% minus 15.6. We will discuss later about probabilities, but I think it is important already now that you understand that from wind data, I can get the probability of not exceedance or the percentage of not exceedance for a given wind velocity in a given direction. And if I want to get the percentage of exceedance, is the complement of the percentage of not exceedance to 100%. So it is just enough that you get this understanding for now, okay? It's just starting from the data. So you download the data and you want to know the percentage of not exceedance of a wind velocity of 20 meters per second. And then you compute the number of times that 20 meters per second was not exceeded, and you put it in percentage terms. And then the percentage of exceedance is the complement to 100%. Do you have any question? Let's forget about probability for now. Just let's reason in terms of frequency, and let's assume that probability and frequency are the same thing. Okay, so at this stage, I know what is the chance of getting a given wind velocity against my ship. Okay, because I mean, if I know that a given wind velocity is exceeded 100% of the time, and I am thinking of the annual max wind velocity. So if I know that the annual max wind velocity is exceeded 100% of the time, I say again, annual max wind velocity exceeded 100% of the time, it means that the retro period is 100 years. Okay? So if it is exceeded 1% of the time, the annual max wind velocity, it means that the retro period is 100 years. Why? Because it means that if I measure the annual max of 100 years, 1% means that only in 1 year I got it. And therefore, the retro period is 100 years. So from the data, this is what I need and what I get. Okay. Okay, so now let me just do this. Just want to. Okay, now let's skip this box on probability because I don't want to treat probability now, just later on. Okay, now I want to remain on the very practical consideration. Okay, okay, now, a second. Okay, good. Let's skip this. And now, let's talk again about terminology. This is more relaxing. You see velocity on the horizontal axis and names of the winds according to what? According to what is called the Beaufort wind force scale. So what does it mean? Hurricane. Hurricane usually implies, we talk about an hurricane when the velocity of the wind is around 35 meters per second. Okay, 35 meters per second means something like 130 kilometers per hour. So you know that with a wind of 130 kilometers per hour, you cannot walk. Usually already at 80 kilometers per hour, it's it's not easy. And or you can walk at 80 kilometers per hour, but you must be very careful with the gusts of 80 kilometers per hour. With an hurricane, I mean 120 means that it's more than 120 actually. It's 130. It means that you cannot walk. When the velocity is zero, we talk about calm condition. And then there is the light air. Light air is about 1 meter per second. Keep in mind that a wind up to 4 kilometers, 5 kilometers per hour is very gentle. When you get wind at 20 kilometers per hour, is already 20 kilometers per hour is already something that it's, it's not easy. And so when we pass to light air, and then light breeze, gentle breeze, moderated breeze, and we are already here at about 20 kilometers per hour, moderate breeze. And fresh breeze, strong breeze, near gale again. Gale is already 60, a little bit less than 60 kilometers per hour. It's already something demanding. And then there is the strong gale, the storm, violent storm, and the hurricane. No need to remember these names for your exam, but in general, keep in mind that when I talked with people working in Harbour engineering, they know these names. They know, and they talked about, of course, depending on the language, different terminology, but they talk very easily about how we have to design. We had a gale, we had an hurricane, we had a violent storm, we had a storm, we had a breeze. The sailors are very, they are very expert about this. So this is why I think the terminology is important if you work on this. Okay, good. Here there is the measurement knots. It is typical for sailors to talk of wind velocity in knots, and even more when they talk about the velocity of a ship. It's very, very frequent. When listen from a sailor, it's very unlikely that they talk about ship velocity in kilometers per hour, meters per second. It's impossible. They use knots. And sometimes they use knots also for the wind. In engineering, we don't use knots. In engineering, as you know, we use the international system, and we don't use knots. Just remember that the relationship is linear, and it's about, very roughly speaking, you take the velocity in meters per second and multiply it by 2, very roughly speaking, and you get it in knots. Okay, and which means that in kilometers per hour, you have to divide by 2, more or less. Okay, more or less. So when we say that the boat is navigating at 20 knots, it means more or less 40 kilometers per hour, which is already a good speed for a ship. And most of the big ships, they travel at 10 knots, just to get an idea. I'm not an expert, but if you are interested, of course, it's very easy to find these numbers. And the conversion numbers, the conversion factors are another thing that is interesting. Keep in mind that in engineering, when you convert units, it is one of the main reasons for making mistakes. Fortunately, if you make mistakes, also in this case, it becomes very clear from the final result of your computation. But indeed, converting units, it seems like a stupid thing. It is a stupid thing, but it is indeed a very important source of error. It is amazing how many how frequent are the errors that we make when we convert units. Okay, good. Ballast, we already talked about it. So ballast tank, and the contour, the bottom of the ship is called the pool, what we call in Italian chiglia. Okay, it's the lowest part of the external body of the ship. And usually in the hull, as I said, we have this ballast tank, which is used to keep the ship in ballast. Important rotational terminology. We say that a ship is in ballast when it is carrying ballast only. And therefore, if it is only loaded with ballast, so if it is in ballast, it's more vulnerable to side winds. And you can understand why if you look at the proportion between the volume of the ballast tank and the volume of the ship. Of course, the ship is more loaded when it is fully loaded without ballast. Of course, when it is fully loaded, usually they release the ballast, the water in the ballast tank. But still, the water line is higher than the water line of the ship in ballast. So usually when we say the ship is in ballast, it means that we are concerned. If there is a strong wind and the ship is in ballast, we are concerned. And therefore, in this situation, people may decide to unmoor the ship because it means that it is too exposed to winds. Therefore, the load over the berths may be really concerning. Okay. Now, so as I said, we need to start from the wind velocity. Wind velocity that we estimate with the wind rows. And we should consider the max velocity of the gust that will affect the considered ship. So max velocity of the gust means the max of the max velocity. So of course, we have to also verify that the resolution, the time resolution of our anemometer allows us to get the bus, the gust, the wind velocity of the gust. And what do we mean for wind velocity of the gust? It means that the measurement should have a resolution of at least 30 seconds. So we define the gust usually as the velocity that is computed, the max velocity that is computed over a 30-second time window. If the resolution of the anemometer is one measure any 5 minutes, it cannot get the 30-second gust velocity, which is the time resolution that is recommended. If the resolution of the anemometer is 10 seconds, then it is easy to get the 30-second gust velocity because I take the average over 3 time windows and then I get the wind velocity over 30 seconds. But if the resolution is longer than 30 seconds, then we cannot get the 30-second gust wind velocity. So once again, when we download our data, we look at the metadata and try to, not try, we get the time resolution because we need what is usually recommended is the 30-second gust wind velocity, which is to be used in the wind force equations that we will introduce now. So here, what you say is another very useful indication. The 30-second gust wind velocity usually is about 20% higher than the average wind velocity over a 10-minute period. This is very interesting to get an understanding of how the measurement can be scaled in time. So let's suppose that you have only measurements at 10 minutes. You may get an idea, not a design, but an idea of the gas to wind velocity at 30 seconds by increasing the measurement over 10 minutes by 20%. This is not to be used for the final design, just for getting an idea, okay? So, for moored ships, most of the guidelines recommend 30 seconds. And of course, you have to refer to the guidelines that are operating in the site. You may find different indications. In the guidelines that I consulted, I found this indication of 30 seconds, particularly in the Port Designer Handbook and also in the Spanish standard. Okay, and one short break for making another consideration about terminology. So we talked about bollards. Okay, images here. Bollards, okay, this is, let me refer, bollard port. Okay, here are the bollards, okay, and they are the mooring point. You see some pictures of the bollards over the field. And this is interesting, let's see. I never saw this figure before. This is a picture of the internal structure. Okay. This is a picture of the iron disposal within a concrete wall, and you see how the bollards are anchored. And of course, we have also to design the size of these iron links, the size of. We have to size also the concrete, and therefore we have to size the percentage of iron, etc. We are not talking about this. This is in the realm of structural mechanics, but it's indeed it is an interesting figure. And then let me just go to Google again. Okay, mooring line. Okay, these are the mooring lines. Okay, you see from the boat here. And one interesting thing are the knots, the kind of knots that they use for the mooring line. And this is another interesting figure, which should also explain the terminology. We will also discuss a more detailed figure, but you see the bow lines, the stern lines, and the spring lines. So the spring lines are those that are inclined at an angle, see, along the longitudinal direction. The bow lines are those that keep the bow fixed, and the stern lines, same thing for the stern. But we'll discuss the terminology later on. And then there is another thing that I want to, okay, I don't remember, but I'll come back later. Okay, so wind forces, some recommendations when calculating mooring forces without closer investigation, the Spanish standard, which is available for download on my website, recommends to adopt a minimum wind velocity of 22 meters per second with a gust factor of 1.2. What does it mean, the gust factor? It means that 22 has to be multiplied by 1.2. It's a safety factor. Okay? Same rules suggest to adopt a minimum wind velocity of 17 meters per second for mooring operations in normal conditions. Okay? And other international standards give different suggestions. And I mean, why, first of all, a consideration, what is the difference between normal conditions and extreme conditions? Of course, normal conditions means that it is what every day is happening, we are experiencing every day. While exceptional conditions means an extreme situation. Usually when we have an extreme situation, we have different procedures and different also traffic conditions. So in normal condition, which is every day, also you have the effect of the fatigue on the structure. So when you have to make precise structure against fatigue and against conditions that have that repeat themselves very frequently, it's a different story when assuming that you have an exceptional condition that happens once every 100 years. And of course, in these conditions, you may also have emergency procedures that allow you to deal with the emergency. So no surprise if here they recommend two different velocities, normal conditions 17 and extreme conditions 22. As I said, I found other guidelines suggesting to go up to 30 meters per second with a gust factor of 1.2 in extreme conditions. On the other hand, I found the recommendation not to exceed wind velocity of 40 meters per second, because usually when the wind velocity reaches a level of 25 meters per second, 30 meters per second, as I said before, usually a way out of a dangerous situation is to unmoor the ships. And therefore, if the ship is left free to move, of course, there is no problem over the berths. And this is a solution that is frequently adopted. Of course, it has to be planned in advance. How to unmoor the ships, the unmooring should follow a very rigorous procedure, because you cannot just release all the ships altogether into a port area. You have to set up an emergency procedure that usually it is included in safety procedures that are approved by the port authority. But for this reason, they say don't go beyond 40 meters per second, because it is very unlikely that you experience a situation with moored ships with such a wind velocity. And okay. Yeah, I was saying oversizing is always to avoid for several reasons: expense, environmental impact. So of course one could say, why not? Why not considering 50 meters per second? No, because it is expensive, there is a higher environmental impact, there is a duration probably of the structure that is lower, because it's a structure that is more exposed to the action of the sea, etc., etc. Okay, good. How to compute wind forces? So I think we can introduce this relationship and then we make the break. By the way, today I'm not planning to make any exercise unless we make a very short introduction to Python, which is another language that I want you to know, at least in the basics. I am planning to make an exercise on the computation of wind forces next week. So we will apply this relationship here. This relationship is conceptually based. It is very simple. If you can recognize there the conceptual approach, so we will discuss it. So what is left-hand side? PW is the wind force in kilonewton. So how should it be computed? By multiplying the wind pressure by the area of the ship that is exposed to wind. I want the wind force, so the force, okay, so very basic consideration of physics, applied physics. Okay, let me compute the wind pressure, and the wind pressure can be easily computed if I know the wind velocity and the density of air. So, like I do in fluid mechanics, if I know the density of a fluid and the velocity with which a fluid goes against a barrier, I can estimate the pressure. So if I know the wind velocity and density of the air, I can estimate the pressure of the wind against the surface. And if I multiply the pressure by the surface exposed to wind, I get the force. This is the conceptual approach. Of course, the wind direction matters, because if the wind is perpendicular to the surface, it is making more pressure. If it is inclined at an angle, the only component that makes pressure is the component that is perpendicular. So the wind velocity, if it is perpendicular, I have to consider the wind velocity. If it is not perpendicular, I have to consider only the component that is perpendicular. And of course, there might be some shear stress. So even the longitudinal component of wind along the surface, there is some shear stress, but it is not so relevant. Okay. So first, there is a coefficient, CW. CW is an empirical coefficient, and we will see what is the recommended value. If I well remember, it's about 1.2, 1.3. It is like a safety factor. It allows to account for uncertainty. And then there must be the area in the formula, and the area indeed is given by two components. So the area of the ship that is exposed to wind is given by possibly two components: the side area above water, okay, and the front area above water, because the wind velocity can be anywhere, any direction. And therefore, I have to consider both the side area and the front area, so the longitudinal area and the transversal area. In fact, when I say side area of the ship above water, projected over the ship longitudinal plane, I get the longitudinal area of the ship. So if the area is carved, I have to project it against the longitudinal plane. Okay. And this is the longitudinal area. But it must be multiplied by a coefficient that depends on the wind direction. Wind direction is expressed here through phi. Phi is the angle of the wind direction to the ship center line. There is a figure which I'll show you. For now, let's just think that it's an angle that is between the wind direction and the longitudinal direction of the ship. Okay, I will show you the figure. By the way, I think it is better if I show it so. Let me see. Here it is P. Okay, this is P. So when P is 0, the wind is aligned with the longitudinal direction. The longitudinal direction is the dashed red line here. Okay. When phi is 90 degrees, it means that the wind is blowing directly against the transversal area. The wind is perpendicular to the longitudinal direction. This is P, perfect. Now, the AW is the side area, and if I multiply the side area by the squared sin of P, I get the component in the transversal, the component against the side area. So if phi is 0, I said, means that the wind is aligned with the longitudinal direction. Squared sin of 0 is 0. So if the wind is aligned with the longitudinal direction, the component on the transversal area is 0. Okay? And then I have to make the corresponding computation to compute the forcing in the transversal area. BW is the front area of the ship, always over the waterline, remember. And I have to multiply it by cos square of phi. Okay, perfect. Now, this is the computation of the exposed area. Between the round parentheses, I have the computation of the exposed area to wind by the two components, longitudinal area, transversal area. Now I have to multiply it by the density of air, or let's say it's, it's the density, it's the specific gravity. And the value is, you see, in a kilonewton per cubic meter is 0.01 more or less, okay? And then there is finally the square of the wind velocity, because you remember that the kinetic energy is proportional to the square of velocity divided by 2g. So you can see here the computation of the energy, the kinetic energy, square velocity divided by 2g. And this velocity is the velocity computed with the probability distribution with a given reaction period, with a given gas factor. So you have a computation of energy multiplied by the density of air, which gives the pressure, multiplied by the area, which gives the area. So pressure times area forcing, and finally the wind force coefficient. We know what is, for a given wind velocity, you see that we know what is the pressure. In fact, we have also graphs available for a graphical computation, which were used more in the past, that for a given wind velocity give directly the final result in terms of pressure, and then multiplication by area is easy. Okay, so this is this formula. This formula, please remember it by memory. It is one of the few relationships that empirical, conceptual, empirical, that I ask you to learn, because something we have to learn, okay? And so this is conceptually based, and therefore I think it also helps to gain an understanding of the physics behind it. Okay. Let me make a break now, and 15 minutes. Do you have any questions?
In realtà perché è anche una sensazione di grande, ma non so, e quindi usare una camera di sala, non c'è le cose in camera, e come non so come fare per sì, sono cioè, nel senso che non importante tutto dall'inizio, cioè fare come insieme a delle aziende, essere esistenziale che stanno così, cioè magari si mettono a sentire ad aprire prima il nostro inizio e ti si esce nella quale non fai insieme.
Secondo me, la troppa spada. I got in the car, and I got to wire and then I said, come on, you're not the gossip boy. Huh? You're not the gossip. But you know, you want to arrest them. He couldn't once. No, man.
Yeah, he asked me advice and stuff like that.
I said, no, I want you to go pass around. And I said,
I don't know what's going on. I'm sure that you were talking and you were like, you were talking with this. What the best thing on the plan? Planning works. Very good. Non mi ristori, don't worry. You don't catch a tiger with a cage. You know, you have to become friends with your tiger. Cazzo di che consiglio hai? Noi sai come qui. Perché you have to put the flowers slowly. Conclusion, you have to become friends with people. Yeah, very something. Maybe it's something perché no,
So now,
Okay, let's make a quick break now. This is lovely. Let's make it lovely.
this is good.
This is the, okay? This. Come la sua cognome? L'ho detto una...
Pallavolo.
No, la pallavolo deve essere questa.
Sì.
Non ha senso. Ok?
Ok, perché è importante.
You want to play pool. If you want to play pool.
Ah,
You know what you can organize? I can give you Milena for this for a while. Okay? One day, okay, you pass by Katrina's house with Milena. No, not by Katrina's house. By University of Medicine, you pass with Milena to make her jealous.
ah.
I can give you Milena for
I don't think that.
She won't be jealous. You think she won't be jealous. This is the problem.
Maybe not jealous, but she's talking about war. So
It's gonna be like
yes. But Milena will never have to speak.
um,
A whore.
Plan B, if Milena says no, we get Fabio. And
Just take it out.
ah,
Just take it out.
no, we also. So, really want to balance it.
Come andate? Non so. Quindi dovevo dire.
Può essere che non ho bisogno di averlo un'altra volta. Ha detto che non ha bisogno di fare un'altra chiedata. Sì, se le avevo vestito. Ma lei lo deve fare. Lei è siciliana. Okay. Key performance indicators. Come on, let's start with this. Giorgio no problem. A lei non la no, perché non guarda. No, ti guarda. Hai finito, no? Okay, it's not looking at What do you think, Thomas? Are you crazy? Or maybe we are crazy.
Maybe you are.
Right, yeah. Probably is lack of emotional intelligence. Because me as a man, when you ask me to break down what I'm feeling, you know, or what I want to think, I don't know what to say. You know, so lo sapevo, non andavo a questo
No. Sì. Chiaro.
Poi,
No, buono.
lei ti ha detto che buono.
No. Buono per bene. Buono.
no, cioè, è il problema. È la problema. E che arriva la io non sei se tu non so, come la vedo? No, mi piace. Sì, ma chi avete qua? Di Mongolia. No. Abbiamo guardato così. No. Cosa difficile?
No.
Io non so farlo. No, non so, io non so farlo.
No, io devo andare a casa, poi devo stare. Cioè, non ti devo stare. Che già sta aperta la vetrina.
Al popolare.
No, non si quando questo perché se provo non ci e domani fate un po', se volete fare il non farlo, faccio per le gare, e domani qui fai quello che diremo alla stazione del comune di l'altro per purissimo.
Io sono un gruppo la Roma, Alberto è nel gruppo di Roma che fanno l'H6, che devo iniziare la presentazione con una discussione gigante. Hai vedere questo. Non so come fa. Non sa come. Sì, no, perché abbiamo incontrato. Sì. A che scopo? Sì. Guarda, mi piace che
Okay, if you don't mind. By the way, I forgot to shut off camera and mic during the 15 minutes. So to make sure that you didn't say anything against me, I will remove that part from the video, okay? But
Against you, nothing.
yeah. So I promise that I will not listen to what you said in 15 minutes, but you have to give me like a couple of days before I can, because I need to remove it, so I need to edit the video, okay? Sorry for that. Okay. So, so we already saw this figure. Let me just get to the website, because this figure, besides giving an idea of how phi is measured, of course, when you talk about an angle between the ship and the wind, you have to specify how the angle is measured, but be careful, because sometimes, depending on the guidelines, you may have a different definition. The same thing for the angle of waves between the waves and the coastline. It's very important when you get data to look at how these angles are measured. Okay, and especially when you download wind data, you know, there is the wind direction indicated with an angle. It is extremely important to understand with what is the reference for measuring that angle. So usually the angle is between the wind direction and the north direction. But just make sure that you get the required information from the metadata. And this figure is also interesting because it gives to you another example of terminology for the mooring lines. So the headline is what I called before the stern line, okay? And the purpose of the stern line, oh, sorry, not stern, but anyway, let's call it the headline and let's make reference to this figure. The bow line, okay? Anyway, the headline is to keep forward part of the ship against the dock. So you need some lines that are aligned at an angle, because if you use the only perpendicular lines, of course, you wouldn't prevent the ship to move back and forth. On the other hand, you also need the perpendicular lines. Perpendicular, I mean like the lines number 2 and number 5, because in case the wind is straight against the longitudinal area, in this case, P would be 90 degrees, the perpendicular lines take most of the forcing. They are the most effective against the forcing that is perpendicular to the berth. Headline and forward breast line keep close to pair, and then the number 5 is the aft breast line, okay? And then there are the spring lines, the forward spring and the aft spring, number 3 and number 4. And they prevent, together with the headline, they prevent the ship from moving back and forth. So this terminology, again, I will not ask this terminology at the exam. It's not really something for the exam, but just keep in mind that this is an essential information for your communication, okay? Now, let me go back to PowerPoint presentation, which is easier. Now, how to compute AW and BW in absence of known values? If the ship is important, you have usually this information from the technical description of the ship. So usually it is something that you find in the documentation, in the ship documentation. But for ships that are less important, you may not have time for this information. And therefore, there are some empirical relationships which can be used, which allow you to calculate the transverse area and the longitudinal area depending on more easily available ship parameters, and in particular, the beam and the length between perpendicular. So it's quite clear that the transversal area must depend in some way from the ship length. So you see AW is expressed as the product of the length between perpendiculars. This is the only case in which we get this, this measure of the ship. Usually we use the length overall for sizing the berth, but this empirical relationship is expressed in terms of the length between perpendicular. And the length between perpendicular is multiplied by the sum of G plus Z. So G is the ship draught. I'm sorry, here there is a link that, let me see if also in the website there is the link that is misspelled. Let me just check. Let me see. Okay, here it is. Okay, no, here it's okay. Ah, yeah, yes. There is a link to be. I need to remember that I need also to change this one. Okay, let's go back here. So it is once again, G is the draught, and sorry, G is the freeboard, and which is the ship depth minus the draft. Okay, so and Z is the mean height of the longitudinal area. So you understand, they take the length, they take a measure of the freeboard, and they take a measure of the height of the longitudinal area, and then they derive an estimate of the transverse area and of the longitudinal area. And BW, the transverse area, is computed in the same way, depending on the beam of the ship, depending on the freeboard, and depending on Y, which is the mean height of the transverse area. These are empirical relationships not to be learned by memory in order to get an estimate of the characteristics, characteristic areas of the ship. And then, so we can simplify the max wind forces by assuming that phi is equal to 90 degrees. Of course, when the wind is perpendicular, you get the max of the wind forcing, and the winds, because the wind blows perpendicular to the ship center line. And in this case, you can write that phi is 90 degrees, and therefore you get that the forcing is given by the product of the wind coefficient CW times the whole of the transverse area times the wind pressure. And the wind pressure is given by the air density times the squared velocity of the wind divided by 2g. So this is just a simplification. And this is the abacus that I mentioned to you. That is a reminiscence of old times. In old times, in engineering, we were used to use a lot of abacuses, and because they allowed a quick computation when automatic computation was not available. And here you can see that depending on wind pressure and depending on wind velocity, and the abacus also reports on the right the definition of wind velocity in terms of our wind classification, the Beaufort wind classification. And you get the two curves, and the upper curve gives the pressure computed as squared velocity divided by 1600. Why 1600? Is just if you make a quick computation on the previous relationship in order to derive directly the pressure, because we are talking here of pressure. And depending on the wind velocity, and you take all the other coefficients together, the product of all the other product ratio of all the other coefficients by assuming the given value for the air density and by assuming G equal to 9.81 meters divided by squared seconds, basically you get 1600. The other curve instead, which gives an higher pressure for the same velocity because the pressure is in the horizontal axis. The lower curve, again, which gives an higher pressure for the same wind velocity, is derived by simply multiplying the velocity by the gust factor of 1.2. And therefore, you get this schematic relationship, and which was used in the past. Just keeping into consideration that the graphical computation, in some cases, is still useful from an engineering point of view, because it gives to you a graphical perception of the results, which is useful because it is, in terms of communication, more significant, a graphical representation with respect to a relationship. So if, for instance, you want to present to a stakeholder, a generic stakeholder, a relationship like this one, I mean, it is less effective in convincing the stakeholders that you used a good solution, that you are presenting something trustable. It is less effective, the analytical relationship, with respect to a graph. The graph is more convincing. This is our experience. It is our experience, and this is why we use sometimes in the dialogue with stakeholders object-oriented programming. Instead of showing a code like R code, we use a block diagram, object-oriented programming, where we show here there is the bird, here there is the sea, and here there is a graph of the wind forcing. It looks like you are more informed. You know that in some of the cases, in some interaction with people, when the stakeholders are very diverse, using too much math or too much mathematics may give the feeling that you are trying to hide between complexity, something that you don't want to see. With the graph, complexity is better rendered. Okay. And of course, you mentioned the analytical relationship and then the graph. It is more effective. And also for the interaction, for a quick decision, sometimes a graphical representation is much easier. You get an immediate computation while going over a PC or a computing machine and then making the computation is sometimes it takes longer. This is why also in civil protection, sometimes we use abacuses in order to understand and to apply procedures. Sometimes we use graphic workflows, like what to do, what decision should I take, and then we refer in emergency situations to workflows because they allow a better understanding of how we need to behave rigorously. Okay, perfect. Now, in order of magnitude, another one. This reference here points out that a modern cargo ship of 30,000 tons, fully loaded, has a wind area of about 15 square meters per meter of length in the longitudinal direction. While the same ship in a ballast condition may have an area of about 20 square meters per meter. And large passenger ships may have wind areas of about 35 square meters per meter. Square meters per meter means area per longitudinal unit of longitudinal length. Okay. So you understand that 35 square meters, let's suppose a long passenger ship, so like 200 meters or 150, or let's say 100, which is more, it's an easier computation. This means that if the length is 100, 100 is not too much. A passenger ship is very easily more than 100. So this ship has a wind area of about 35 times 100, 3,500 square meters. So if you go here, the wind pressure is about, let's take a wind force, let's take a moderate gain, okay? It's here. So here I get a wind pressure of about 0.2 kilonewton per square meter. So 3,500 times 0.2, it means 700 kilonewton, I think, if I'm not wrong. So it means 700 kilonewton means a forcing of 700 kilonewton. It's a forcing of 75 times, I think it is 7,500 kilograms, if I'm not wrong. In a way, it is a significant forcing. Okay, so if you try to make a very quick computation, you understand that it's significant forcing, that usually it is loaded over like 4, 5, 6 bollard points, mooring points, 6 bollards, with a subdivision of the forcing over the bollards, which is not in equal parts. It depends on the orientation of the mooring lines. We will see how to compute the forcing on each mooring line. And I mean, it is a significant forcing which justifies, on the one hand, the diameter of the mooring lines. If you notice their diameter is extremely significant. These mooring lines are elastic, they are not static, for obvious reasons, because, of course, with the static, with the dynamic constitution, they can absorb better the gusts of wind, but this means that the computation of the mooring forces has to take into account the dynamic behavior of the mooring lines. So it is not easy to make this computation. We will make an example with an exercise, but it is interesting. It's not an immediate computation. And also, you understand that the mooring point is to be sized with a good, with a strong approach, very rigorously, and it's something that really needs to be very strong. Okay. Now, if the wind blows at an angle, which is the usual situation, there will be a transverse and a longitudinal load component plus a rotational moment. This is what we talk about now. So if the wind, once again, it is at an angle, even if, by the way, even if the wind is perpendicular, you may get a rotational moment, and we will see why. So, mm, so what is the distributed load given by actually the relationship that you see on the screen, caused by wind along the direction X, the direction X is the direction of the berth, okay, along the berth, on the berth structure. So you have to compute, first of all, the component along the berth of the wind forcing, and it is indicated here as PWX. And X actually can be, yeah, it is along the direction. And then you divide it by the length between the mooring points. So usually what we do is to size each mooring point. Okay? And in order to size each mooring point and each mooring line, actually, you have also to size the section of the mooring line. In order to size it, you need to compute the forcing on each mooring through a decomposition procedure that I mentioned to you earlier. And then you have also to compute the distributed load along the berth, because it's not just enough that you size the mooring point. You have also to size the iron part of the concrete of the whole berth structure. So you have to make sure that the moving point is really fixed to the berth, and you have to make sure, in a second step, that the berth resists to the whole body of the berth resists to the forcing. I mentioned the rotational angle. Yes, this is important because in order to compute this distributed component is not really. But in order to compute the distribution of the forcing along the mooring lines, it is important to know the rotational. I mentioned that there might be a rotational moment, sorry, I wanted to say. There might be a rotational moment even if the wind blows perpendicular to the ship. Why? Because here works. You check. Yeah. Okay, we are there. So if you are actually like this one, okay. And let's suppose that this is the part of our water, okay. Here actually, here, the water body. And this is an A. Let's suppose that the wind blows just perpendicular to the magnet. So that the wind blowing like here. And it actually means that you get in the black hole. Why I put the forcing concentrated here? Because the forcing is concentrated in the center of gravity, this geometric field defining AW. Okay, here probably the center of gravity, if it is here, I think something also here, okay? Then the center of gravity is like here. But this doesn't mean that the boat, if unmoved, would simply move along the wind direction. Because if I look at the ship from the top, this is the ship from the top. This is wind. This is the so maybe that's the noise with my finger. It's measured here. It is measured here. For you resting my finger. So, yes, it's measured. So, so you may expect something like this is the center of gravity. Okay. Here. I expect that the shape just moves here. Okay. Actually, any shape, depending on depending on the geometry of the shape, if it is hit by wind, it tends to rotate around a point which is a behavior, it's an inherent behavior of the shape. So the axis, the rotational axis, the vertical rotational axis, which this direction is out of the black group is vertical. It is an inherent behavior of the shape, which means that if you get wind in this direction, the shape doesn't necessarily rotate around the center of gravity of the longitudinal area. It rotates around the vertical axis, which is an inherent behavior, and whose position depends on the velocity of the ship. If the ship is in a stable situation, the velocity is zero, the rotation is different with respect to the ship that is moving forward. Because of course, when the ship moves forward, the geometry will decidedly changes, and then the rotational axis will change. In particular, when the ship moves forward, if I remember, the rotational axis moves back. And then, if the rotational point, the rotational axis is here, of course you have the forcing here, and which turns into and if we want to compute the forcing on the moving lines, is of course we need to know not only the result of the forcing, but also need to know the rotational moment. Because if you have a rotational moment like this one, of course you get difference from here, with respect to here. Okay. So this point, the next question is how we identify this rotational point, which is called, by the way, pivot point. As I said, it's an inherent behavior of the ship. I think this is the subject of the next slide, and okay, let me go to the web page because I get better oriented. Here we are, because there are some figures which I'm not sure I have in the slides. Okay, so you see vessel rotation, okay, and where is it? Just 1 second. Oh, here it is. 1 second. Okay, I think I anticipated too much because this is indeed important when you compute the forcing along the mooring lines, which is a bit later. Okay, and before than that, it's better if I follow the workflow, if I follow the thread of the web page. So let's postpone this. How to compute position of the pivot point, how to compute the rotational moment. The rotational moment, of course, it's clear how to compute it because there is a distance like eccentricity between the also there is this distance here. here on the page, but let me just postpone this because it's urgent. For now, let's move forward, restarting from the computation of the distributed load. This is clear. I mean, once that I have the component of the wind forcing along the direction of the birds, I can compute the distributed load. Okay. Now, I think that this is something that we already discussed. Okay. This is interesting. 4 pairs were the third statement. 4 pairs where ships can berth on both sides, which may happen. The total wind load acting on the pier should be approximately the wind load on the largest ship plus 50% of the wind load on the ship on the other side of the pier. So basically, clearly, if you have a pier with ships along the both sides, so this is the pier, okay, and you have a ship here, and a ship here. Okay. So the suggestion is they move the largest ship here, or if you have more than one ship, get the total load, and here on the other side, you get over 50%. Why? Because clearly, if you get wind in one direction from the other side of the pier, you get less wind, because it's already screened by the first point, okay? So it would be too much to take the full load on both sides. These indications are all derived from my references, the Port Designer Handbook and the Spanish one. Once again, these are guidelines that you have to check. You have to check depending on the location where you are making your design project and depending on the international regulations or local regulation or local laws in force. So check them, of course. Okay, we already discussed the terminology of the mooring lines. So I think we can skip this. And in general, as I think we can also skip this because I talked about a wind drift and rotational moment. Drift means the resulting force of the wind. Okay, so this is the drift. It is the resultant, the sum of the forcing along the wind direction, and there is a rotational moment. So the wind drift is forcing in the direction of wave propagation. Okay, that's fine. So, and then here it's time to understand the dynamic of vessel rotation then. So we need to define the pivot point. The pivot point, let me define it. It is the point around which the ship appears to be turning for an observer starting on board of the ship. Okay, so if I am on board, I get a feeling that when I am on the pivot point, I am rotating around myself without any movement, okay? So I am just rotating around an axis and I'm not depicting in my rotation a circle. Okay? So it is defined based on the feeling of an observer standing on board of the ship. Now, this is the interesting consideration. For a resting vessel, velocity 0, the pivot point is located in the center of gravity of the underwater body of the ship. Why the underwater body? Because the ship rotates by generating a pressure on the water around it. And therefore, it's clear that the rotation axis of the ship must be located in a way that the pressure against the water is uniform. And therefore you have to refer to the part of the body of the ship that generates pressure over water. So it is the underwater part of the ship. So you get this underwater part. You get the center of gravity, it is a volume. It is an underwater volume. You get the center of gravity of it. And this is the location of the pivot point. And the rotational axis is the vertical axis passing through the pivot point. Now, you understand that if the vessel is resting, is one story. If the vessel is moving, the volume, the underwater part of the ship changes. And in particular, if the vessel is moving, you have the frontal part that is raising a little bit. And the stern, the opposite part of the boat, the rear part of the boat, goes a little bit more underwater. And therefore, the geometry of this volume changes and the center of gravity changes. So basically, when the vessel moves forward, the position of the pivot point here shifts forward. For typical velocity, the pivot point will move about to 1/4 of the length of the vessel from the forward. Okay? And when the vessel moves astern, so backward, the position of the pivot point shifts at about 1/4 of the length of the vessel from the stern. The stern is the rear part, the bow is the frontal part. So the bow is the prua and the stern is the popper, traduced in Italian, translated in Italian. So rotation is originated when the center of gravity of the windage area, also called windage area, the area exposed to the wind, is not the same as the pivot point. Fine. Of course, sorry, I go back a little bit. Of course, we need to refer to again to the documentation of the boat, which usually provides information on the pivot point, which is of course something that is very important, and gives also information on the movement of the pivot point depending on the velocity of the ship. Okay, and I think this is all for wind forcing. The next slide is already about wave forcing. Okay, just let me check if there are questions on the chat. And by the way, do you have any questions? Okay, perfect. Okay. Let's move forward. Wave. Okay, very quick premise. We have okay. We have the same approach with respect to wave forcing and the same or a similar approach with respect to wind forcing. Just give me 1 minute because I have to check. Okay. So we have a similar approach with a similar empirical relationship. We don't go into much details. Keep in mind that it is quite frequent that I ask the question how to compute wind forcing at the exam. It is usually I don't ask anything related to wave forcing and current forcing. You will understand why, because there is a larger portion of empiricity in in the computation. Okay, so first of all, we need data on waves, and we know that, okay? And here there are some consideration on the minimum length of the observation period. Let me make some consideration on this. So when I talked about the similarity between frequency and probability, it is quite, obvious to understand that when you compute frequency over data, the computation is more reliable if the database is more extended. The longer the database, the longer the observation period, the period covered by the database, and the higher the reliability of the computation. And of course, indeed, this similarity between frequency and probability, if you think of it, and if you think of the limitation of this similarity that I discussed with you, it's clear that this similarity holds in a more reliable way if the observation period is very extended. It is like estimating the probability of getting an egg by tossing a coin on the basis of tossing experiments. You understand that if you toss just once, you don't get a good estimate of the probability. We know from the theory that the probability is 50%, very basic theory, okay? Very basic intuition of the theory. But indeed, we know that it is 50%. But if you make only one experiment and you toss only once the coin, you cannot absolutely say that the frequency is equivalent to probability. Because the frequency will be one experiment, you may get either I don't tell you, but the frequency 1. If you make 2 experiments, it is very likely that you get the same, like, and you would again estimate a frequency of 1, which is not equivalent to the probability. If you toss the coin many times, then you get a good estimate. By the way, what I'm saying was the subject of an interesting debate in statistics. I think it was in the 19th century, and a famous statistician, Pearson, in order to prove the reliability of this statement, in order to demonstrate the similarity between frequency and probability, he tossed the coin 24,000 times. It doesn't take so long, maybe 1 week, I don't know. And he got 12,000 plus 24 times 5. And he demonstrated that with a very long sample, and we provided the interim results in the progress. And he demonstrated that the longer the sample, the longer the more established the similarity between frequency and probability. So this means that if you indeed work with data and you estimate frequency with data, both for wind and for waves, here we are talking about waves, you have to wonder what is the minimum length of the observation period, the observational period. And what is the minimum? Here you see an indication. So the very minimum, the very, very minimum should be 1 year. 1 year allows you to browse only one season. Only one season. It is the very minimum. Okay. Of course, if you don't get to 1 year, you are losing one season, which is not ideal because, you know, you can never exclude. Of course, we may say during summer, during the warmer season, it's difficult that you get a wave storm, but it's not impossible. So 1 year is the very better, 5 years. Usually, also in other statistical environmental application, we say that 5 years is the very minimum. Of course, it depends. This very minimum depends on the variability of the process. You may have processes that are characterized by a very reduced variability. So you may have wave weathers that are characterized by a very, very small interannual variability. This means that with 5 years, it's more than enough. If the interannual variability is large, which means that it may happen that you get 1 year with absolutely no storms, and then I hear with a lot of storms, and then again maybe a lot of storms, and then no storms, Variability means that the data are not concentrated around the average, they are very spread, then you need more here data. This indication that you see here, very minimum is 1 year, and 5 years as a period that delivers a useful characterization. Just be careful and keep in mind the specific behavior of the process. Okay. Now, first, we have also to take into account wave breaking. We have to avoid wave breaking into a port, into an Harbour. Okay. You know what is breaking? Breaking is a point where you get the energy of the wave, or let me better see it. It is a point where the wave traveling, which is a travel of energy, not a travel of mass. So when you have wave movement, this is a movement of energy. You know that a single particle fluid don't move forward or back. There is a very small rotation of the particles, but it's very negligible with respect to the movement of the energy. After breaking, the movement of energy, the flux of energy translates into a flux of mass. And therefore, you understand that we have to avoid this. We have to avoid wave breaking, also because wave breaking occurs when the lower part of the wave gets very close to the bottom of the sea. And therefore, this is dangerous for a moving ship, because it means that the bottom, the hull of the ship may crash against the sea bottom. So we need to avoid this situation. So what is a criteria to determine if breaking occurs? Usually we use the relationship that is presented here. So dB is the sea depth, and HB is the individual wave height. So if we see that the wave height is such that it gets close, this is clear, get close to the sea bottom, then this is a problem. We have to avoid this situation. So first of all, let's take into account, before computing the wave forcing, that after we identify the wave height, we need to check that breaking doesn't occur. Okay. Perfect. Now, another important consideration, when there is the need to compute wave forcing, we don't take has extreme wave height, the usual design wave for a given retro period. We get a more reduced value. And why? Because usually the wave forcing is a lower order of magnitude with respect to wind forcing. And therefore, usually the berths are already projected for a wind forcing that is higher than the wave forcing. Of course, they may occur contemporarily, but on the other hand, it's also true that it is reasonable that when computing the concurrency factor, when you take into account the concurrency of the two forcings, it is reasonable that we are suggested to reduce one of the two, and it is reasonable that we reduce the lower one. Okay, so I mean, adopting a reduced design wave height, as you can read here, may increase the risk of flooding, of course, because flooding occurs when the wave height reaches the surface of the berth. But this may be justified by reduced construction costs, as long as it does not decrease the safety of the personnel. So let me explain better. One thing is to take a design wave height for estimating the wave force. Another thing is to estimate a design wave height to avoid flooding. So if we want to avoid flooding, then we have to take the max wave height plus a safety factor to determine the level, the altitude of the berth. So if we really want to avoid flooding, then we have to take the extreme wave height in order to determine the height of the berth. But for the computation of the forcing, usually we reduce it. Okay. Of course, flooding may be fine as long as it does not decrease the safety of the person. So you may get a damage after flood, but the damage may be compensated by reduced construction costs. So this is what we do for urban drainage systems. Urban drainage systems are designed for a record period varying between 2 years and 10 years. Instead, when we design a bridge, we work with a record period of 200 years. Why? Because urban flooding is not as dangerous. But in urban flooding, when we suspect that there is a risk of loss of lives, then we increase the record period. Okay. Good. Now, of course, we know what are the behavior of the waves in a port and what are the factors affecting this behavior. So the bathymetry, we already talked about it. And reflection of waves, we will talk about explicitly about reflection of waves and possible resonance. When the waves get reflected by a wall, we get a reverse wave traveling towards the ocean, and we have to make sure that the two waves don't superimpose, because if they superimpose, they can generate Harbour oscillations, which are extremely dangerous, and they can break any mooring lines. So if you get resonance, it's called resonance on Harbour basis, it means that the reflected wave is superimposed with the incoming wave, and then they can break any mooring line. There is no way if you get resonance, because the wave height is progressively increasing. And therefore, we have to take into account this process and to be very careful. We will dedicate a lecture, which is not easy, because you know that study resonance is really not easy. It's really not easy. These are processes that are extremely, complicated, but indeed these are processes that can originate what are called the rogue waves. Rogue waves means monster waves. And sometimes also in open ocean, it happens that monster waves are generated. And this explains the scene of very huge boats in very particular situations. Because also in open ocean, it may happen that wave get into resonance. And usually this happens when you have train of waves collapsing. We are used to study a plane wave, which is a single wave traveling. But in open oceans, you may get train of waves that meet, and if they superimpose each other in resonance, then they can originate a monster wave. And we have observed some examples of waves that are like 35 meters high, and you understand that this may be dangerous even for the largest ships. And also in the harbors, we have to take into account this possibility that we get wave resonance. Okay, and also we have to take into account reflection, sorry, and wave shoaling, which means that the wave height is progressively increasing when the waves get closer to the sea bottom. Okay, so At the end of the story, design weight is estimated for a given retro period, which is, how it is defined. And again, the design retro period should be determined by considering the consequences given by a given design wave. And when human life is at risk, the retro period is never lower than 100 years. And let me spend a few more words about the retro period. And because I want to make a consideration, which is, I think it is interesting. So, retro period is related to probability, to frequency, because we skipped talking about probability. So let's talk about frequency. If we have a long series of data, this is fine, okay? And retro period is the average time between two events that have an intensity that is equal or higher than a given one. But there is an interesting question related to retro period. If the retro period is 100 years for a given design, what is the probability/frequency to get that event in 100 years, which is not one? So once again, let's suppose that you size alerts against an event that is a retro period of 100 years. Then, in 100 years, what is the probability of getting that event? It's not one, because you are never certain that a random event occurs. Okay? Of course, you may reply, well, in the long term, the probability of the event to occur tends to one in the long term. But how long? So what is the reply to my specific question? What is the probability in a time span that is the same as the retro period of a given event to get that event? This is interesting because, in particular, if you have to make a cost-benefit analysis, because take into account that when there is flexibility, definition of the retro period, usually it is defined with the cost-benefit analysis. When do we have flexibility? Not when the human lives are at risk, but when the occurrence of an event, the impact of an event is just economic damage. I could make a cost-benefit analysis, like what is the cost of getting protected against an event that has a retro period of 200 years, and what is the expected damage? Okay. So the probability of this hypothetical event occurring in a time span as long as the retro period is interesting. Now, so first of all, let's refer to the annual max wave height. We are talking about frequency. Okay, so let's refer to the annual max. So our data set is the annual max wave height. And the first, let us recall the relationship between probability of not exceedance and retro period. P is equal to T minus 1 divided by T. So if the retro period is 100 years, then the probability of getting this event is 99%. Not exceedance, sorry, not the probability of getting, the probability of not exceedance. So I state again, because I want to be clear. If the retro period is 100 years, the probability of not getting in a given year that event is 99%. So the probability of getting it is 1%. Perfect. But for a period of n years, lowercase n, what is the joint probability of not getting the event? Sorry? No, it's you look at the second relationship. So if the probability of getting so that's a reason in the square like this. Okay, let's refer to tossing a coin. Okay, so the probability of that is this is different as a probability of fixators because this is binomial distribution, but in order to understand, the probability of that is 2.5. This means that you toss whatever you find, and the probability of getting that is 1.5. What is the probability of getting 2 in 2 tosses? It's 0.5, it's equal to 0.25. Okay, now let's refer to this relationship. The probability in 1 here. So let's put it, let me use a better notation. P1 is equal to T minus 1 divided by T. Once again, here the event is under maximum mean height. Okay. Now, in 2 years, what is the probability of getting it? It's again to the power of T minus 1 divided by T power. Okay. What is the probability of T? Is equal to T minus 1 divided by T, the power of T, which I think it is probability of 63. So you can get here the explicit relationship for T, but it is for T, but let me just see the graph here. So this is the lifetime of the structure, and this is the retro period. So let's get the retro period of 100 here in the vertical axis, and you go to the lifetime of the structure to 100. You see that it is marked by the probability of 63%. Okay. So the probability of 63% marks the equivalence between lifetime of the structure, so the period, n, lowercase n, and the retro period. And then you see that so we have during a time span equivalent to the retro period, a probability of getting of 63% of getting the event. So if we want, and this is the interesting consideration, if we want that to reduce the probability during the lifetime of the structure, to reduce the probability of occurrence to 10% of the event with the retro period equivalent to the lifetime. So if the design lifetime is 50 years, we should design for a retro period of about 500 years. If we want in this 50 years to reduce the probability of this event to 10%. Because of course, during one specific year, you have a very low probability of getting an event that is equivalent to the retro period. But as the number of years increases, then you have to increase it. So basically, this provides to you an explanation why the retro period is very often larger than the expected lifetime of the structure. If you want to minimize if there are people at risk, we need to increase it because otherwise it's too much. So if people are at risk, and the expected lifetime is typically 50 years, because for a birth is no more than 50 years, but a probability of 63% of getting people at risk in 50 years is too much. And this is why we designed the births for like a return period of 200 years. This is an interesting game of probability, you know. Game with probability, you get this. Okay. You see here the last sentence. When we design dams in hydraulic engineering, usually we take an expected a return period of the design of 1,000 years. You understand why? Because, I mean, failure of a dam, collapse of a dam, is something that we really want to avoid. The lifetime of a dam usually is no more than 100 years. Then there are some dams that may last for 200 years, but usually it's much less than that. It is about 100. After 100 years, a dam usually is closed. It's no more used. It's deep left, which means that if there is still a reservoir, it's emptied, and we don't use the dam anymore. But very often, after 100 years, the reservoir is completely filled by sediments. Still, we designed the dam for a return period of 1,000 years. And so, if the design of a birth is implying a disaster, if there is a collapse, then the return period should be really large. What is the problem? The problem is that when you want to estimate a design variable, a project variable, a forcing for a return period of 1,000 years, you need a much long observational record, otherwise it's not reliable. And this is why when we design dams, besides given that we don't have long records for rivers, about 50 years, and with waves we have even less than that. This is why we, besides adopting a very high return period, we also use safety factor. Okay. Now, keep in mind that there is also wave direction that is important. So it is not, usually we consider a plane wave for a given direction, but with harbors, if there is a significant probability that we get waves along any direction, then we have to make our analysis for any wave direction. And for this any wave direction, we have to compute the significant wave height, which I think you know what is. It is the result of our assessment of the expected wave height for a given return period. Now, some rules of thumb, again taken by the Spanish standard. So, if we have ships with displacement of 3,000 tons, up to 3,000 tons, which means no more than that. So the significant wave height, so the wave height that we take as a project variable should be of the order of magnitude of, for pleasure craft, 0.4 meters, for fishing vessels, 0.6, and with fishing vessels with a length overall higher than 30 meters, 1 meter. For an harbor, I mean, for an harbor, 1 meter of wave is a wave. I mean, it is significant because the harbor is a sheltered area. So keep in mind that you have also this complication that observations should be taken inside the harbor. So if you have observational waves in the open sea, then we expect that inside the harbor they are softened, they are smoothed, and therefore, I mean, 1 meter into the harbor is really lot. And this rule of thumb, this indication is increased to 2 meters for ships with a displacement greater than 3,000 tons. Because I anticipate the relationship that I will present to you now for the computation of the wave forcing depends on the wave height in the same way as the wind forcing dependent on the wind velocity. Okay, so we will get now a relationship with the squared wave height as an estimate of the energy of the impact of the pressure of waves against the ship. And therefore, it's important to adopt, of course, a wave height. Okay, now, wave forces, and they are originated by the movement of the ship that is caused by wave action, of course. And the ship is a rigid body with 6 degrees of freedom. And I will show you this figure with more detail. And in fact, the motion of a ship at sea has the 6 degrees of freedom of a rigid body. And it corresponds to translation along the 3 directions and rotation around these 3 directions. So 6 degrees of freedom. And then let's make a focus on terminology. Okay. So once are impacted by waves, of course, we already said we can have a rotational and translational motion. And we can identify these 3 axes, the longitudinal axis, the vertical, the transverse axis, and the vertical axis. So the rotational movement around them are rho for the longitudinal axis, pitch for the transversal axis, and yaw for the vertical axis. So you may have heard, for instance, about the pitch expected for a boat when the boat accelerates, and the pitch is the rotation around the transversal axis. The roll is the rotation around the longitudinal axis, and the yaw is the rotation around the vertical axis. And the translational motions are heave, sway, and surge, respectively. Okay? And here you see the figure with all of these notations. Okay. So, guidelines. So, mooring line forces are induced almost entirely by waves of period longer than 20 seconds, with major contributions during the period range 50 seconds, 200 seconds. Of course, when we refer to waves and when we determine the significant wave height, we have also to refer to the period. We observe waves and there is a relationship between the wave height and the wave period. Okay, the problem is that different forces are originated by different critical forces are originated by waves with different period. Rolling is triggered primarily by swells with a period of 13-19 seconds. Pitching is small usually and is insensitive to the wave period. If we talk about heave motions, this tends to be equivalent to the wave height at long periods, and pitches are, heaves are smaller with short period waves. This is quite obvious if you think of it. Okay. And here is the relationship. Let me check if I can get it from the website, because I can make it larger. This is a figure about rogue waves, and you see that it is placed in along the Earth, and it is a warning because actually it happened that people were drawn by rogue waves. And rogue waves are not only related to tsunamis. Of course, during a tsunami, you get this sudden wave approaching the coastline, but they can also originate, as I said, they can be originated by collision of train of waves or other phenomena. It is interesting to look at the Wikipedia page of it, which is here. You see a picture here, and freak waves or killer waves, large and unpredictable surface waves that can be extremely dangerous to ships and isolated structures, such as lighthouses. And they are distinct from tsunamis. I think there are also some pictures somewhere. These were only recently discovered. This Wikipedia page is nice to read. Okay, so let's. Too many windows open. Just 1 second. Okay, here we are. Let's get the relationship. We have about 10 minutes to go. Here it is. Okay, good. Let's see. Very good. I forgot to mention, when I talked about wind forcing, I forgot to give a value for the wind coefficient. I think it is about 1.2, but you can find the value in the web pages. Okay, so lateral or transverse wave force and longitudinal wave force. So there is a coefficient. Here it's called CFW. It is called water plane coefficient, depending on the wavelength LW at the location and the ship's draft D. There is a figure which is given later, an abacus, from which you can get the value of this coefficient. There is another coefficient, CDW. It's a depth coefficient, which depends on the wavelength and the water depth at the location. And again, there is another abacus to give this coefficient. It is expected to increase when the wavelength is comparable to the water depth. Gamma W is the specific weight of water. It is the counterpart, the equivalent of air density. Remember that fresh water has a density of 1 ton per cubic meter. Seawater, usually the conventional value for the specific weight of seawater is 1.024 tons per square meter, so 1,024 kilograms per square meter. Here it is reported a value of 1,034 kilograms because it refers to a more salted water. HS is the design significant wave height, which is squared. Okay, so once again, you have an estimate of energy. you may remember that the energy that is transported by a wave is proportional to the square of the wave height times the density of water. And P is the angle of the wave direction to the ship center line. So it is an analogous angle analogous to the one that we consider for the wind forcing, and that's it. Okay, and this is the lateral wave forcing. Okay, here there is this terminology transverse wave forcing, which is I found it reported in a guideline, but it is a bit misleading. To be clear, lateral means the wave forcing on the longitudinal side of the ship. And then we have the analogous for the longitudinal wave force, which is against the stern or against the bow. And here you have the estimate that depends on the cosine phi. And that's it. And here you have the two abacuses. Okay, this is for CFW on the left and CDW on the right. This is taken from the Spanish standard. So once again, W here is wavelength and CW is the coefficient. So you see that for H is the depth of water, depth of sea. And so you see that for increasing wavelength, we get a higher coefficient. And for increasing water depth, we get a lower coefficient. This is the opposite of what I said before. Sorry for that. And it is a bit counterintuitive. Once again, you don't have to learn by memory this relationship because it is less intuitive. And then the relationship that I gave for the wind. This is taken by the same reference. And but anyway, you don't need to learn it by memory. I think that it's the case to stop now for today, because resonance we will take, okay, we'll talk about it later. Next time we will make an exercise on the computation of the wind forcing, yes, wind forcing. Questions? Okay, thank you. Let me just start. Sorry? Sorry? Yeah. I remember that.